Dear students, we'll talk today about the Euler's phi function. Let us first define the reduced residue system modulo a number m. Reduced residue system modulo m, where m is any number greater than 1. It is simply the set between 1 to the set of all numbers between 1 to m which are relatively prime with m. Yes, the set of all numbers from 1 to m which are relatively prime with m. That set is called a reduced residue system modulo m. For example, if m equal to suppose 6, then the set 1 and 5 is the reduced residue system modulo 6. This thing we have already discussed in our classwork. Now, we'll now define the Euler phi function. It is denoted by phi. It is simply the number theoretical functions. The number theoretical function defined by this phi of m is equal to number of elements in the RRS modulo m. So phi m is the number of elements in the set RRS modulo m. In simple terms, it is the number of elements from 1 to m which are relatively prime with m. For example, as we have seen above, for m equal to 6, phi of 6 is equal to 2, because there are only two numbers which are relatively prime to 6 between 1 and 6. Now this phi function has many important properties. We'll discuss some of them here. So जो सबसे पहला result है theorem 1. So it states that if p is prime, then phi of p is equal to p minus 1. And conversely, if p is an integer, p is an integer such that phi of p is equal to p minus 1, then p is prime. The result बहुत easy है. The first part is in fact obvious, because if p is prime, then the number of elements in the set from 1 to p which are relatively prime with p is obviously p minus 1, because all the numbers from 1 to p minus 1 are relatively prime to p, and hence phi of p is equal to p minus 1. Now again, for the converse part, suppose now phi of p is equal to p minus 1, then p must be prime, because if p is 1, phi of 1 is 0, phi of 1 is 1, so it cannot be equal to p minus 1. Now if p is not prime, that is p is a composite number, then there is at least one divisor of p lying between 1 and p minus 1. So there is a divisor d which is greater than 1 and less than p minus 1, and this d cannot be therefore relatively prime to p. Hence the number of elements between 1 and p minus 1 which are relatively prime with p must be less than p minus 1. So p must be therefore prime if phi of p is equal to p minus 1. So in fact हमारी ये कोशिश है कि हम phi of n निकालें कि what is the value of phi of n. Otherwise कि अगर n large number है, एक बड़ा number है, it is not easy to find phi of n in general like this. So we will try to devise a formula to find the value of phi of n in general. तो इसके लिए पहला setup है. So the next setup is the following result. This is theorem number 2. So we'll now find phi of p, phi of some prime power. That is, let p is a prime, p be a prime number, p be a prime number. Then we have the following: phi of p power m is equal to p power m minus p power m minus 1 for any positive integer m. So if m is any positive integer, phi of p power m is equal to phi p power m minus p power m minus 1. So again, for the proof, again it is easy. So we have to check the number of elements between 1 and p minus 1, which are relatively prime with p power m. So let us go the opposite side, that we will check the number of elements between 1 and p minus 1 which are not relatively prime with p power m. So what are the numbers which are not relatively prime with p power m? In fact, they are given by p, 2p, 3p, so on, up to p power m minus 1 into p. So these are the only numbers between 1 and p power m which are not relatively prime with p power m. And you can see easily their number is, the number of such elements is p power m minus 1. You can check 1, 2, 3, so on up to p power m minus 1. And hence phi of p power m is equal to total number of elements minus the number of elements which are not relatively prime, that is m minus 1, and hence this proves the theorem. So we can now find, therefore, by this formula, the value of phi of any prime power. For example, phi of 7 power 3. So by this formula, it is equal to 7 power 3 minus 7 power 2. And you can check, it is 343 minus 49, which is equal to 294. Now, general जाने के लिए, to find value of phi m, we need a result, but that result needs the Chinese remainder theorem. तो जो हम आगे करेंगे, तो इस वक्त वो रिजल्ट हम सिर्फ स्टेट करेंगे और इसका यूज़ करेंगे. So the result is the theorem 3. So before stating this theorem, we have to define a new thing, that is a multiplicative function. So इससे पहले हमें एक multiplicative function define करनी है. Multiplicative function. So we say a number theoretical function, any function, number theoretical function, which means a function from n to n, is a multiplicative function if phi of m into n is equal to f of m into f of n for any m and n numbers such that they are relatively prime. So if a number theoretical function satisfies this property, we say it is a multiplicative function. So the theorem 3 states that phi, the Euler's phi function, is in fact a multiplicative function. That is, for mn equal to 1, phi of m into n is equal to phi of m multiplied by phi of n. जैसे ये रिज़ल्ट हम सिर्फ अभी यूज़ करेंगे, तो इसका प्रूफ हम आगे के लेक्चर्स में देंगे जब हम चाइनीज़ रिमाइंडर थ्योरम प्रूव करेंगे. So now using all these results, we will be now able to find the value of phi for any general value n. So this is the theorem 4. It states that if n is any number which has a canonical representation, suppose it is n equal to alpha 1, p2, alpha 2, and so on, pk, alpha k, where obviously these p1, p2, so on, pk are distinct primes, then this theorem states that phi of n will be equal to n times 1 minus 1 by p1 multiplied by 1 minus 1 by p2 and so on, 1 minus 1 by pk. So let us prove this first. Now we know we have by theorem 3 that Since the P1, P2, so on Pk are distinct primes, so they are relatively prime. Pi and Pj is always 1 for all I not equal to j. And also we have phi of Pi power alpha by above result. It is equal to P power alpha I minus P power alpha I minus 1. And we can write this in the form P power alpha I into 1 minus 1 by Pi. So since phi is a multiplicative function, if we apply phi to n, we have phi of n is equal to phi of P1 alpha 1, phi of P2 alpha 2, so on, phi of Pk alpha k. And this gives using the above fact that phi of Pi alpha is equal to Pi power alpha into 1 minus 1 by Pi. We get will be P1 alpha 1 into 1 minus 1 by P1. In place of this we have P2 alpha 2 1 minus 1 by P2, so on, and in place of this we have Pk power alpha k into 1 minus 1 by Pk. So rearranging these terms, so if we combine this P1 alpha 1 multiplied by P2 alpha 2 multiplied by Pk alpha k, it is equal to the number n. So we can write it n into 1 by P minus P1, 1 by 1 minus P2, and so on, 1 minus 1 by Pk, and this proves the theorem. So we can apply this theorem, for example, to any number. If you have, suppose, example, suppose our n is 200. 200 we can write in the form. If we factorize it, make it canonical factorization. This is 2 power 3 into 5 square. Yes. Therefore, what is phi of n? Is phi of 200. By result, it is 200 multiplied by 1 minus 1 by 2, 1 minus 1 by 5, and which is equal to 200 multiplied by 1 multiplied by 4 divided by 2 into 5, which is equal to 10. It is only 20 multiplied by 4, that is 80. So phi of n is 80. Therefore, whenever we know the canonical factorization of n, we can find the value of phi n. In fact, you can see here, we even need not to know the powers of p's. We just need to know all the prime factors of n. Then we can calculate the value of phi for any value of n. So in the next lecture, we will discuss some more properties about this phi function. Thank you.